So we've made it. We're now at our last section of brief calculus. After this, we'll start into our review sessions where I will post some quizzes with questions that'll be similar to the test. They're going to come off the test review. So we'll keep moving forward. So let's take a look at our last section together. After this, we'll be completely reviewing what we've been doing. Okay, so here we are. So this last technique is called improper integrals. So what is an improper integral? Well, let's define what we've been doing so far. Proper integrals are, remember, the f of x is some function that is a rate. It's a derivative of something. And we can integrate it between two limits, a and b. Okay, and what that gives us is it gives us the area under the curve between a and b. So we've got these bounds a and b that are finite. They are some set amount. Okay, they don't go on forever. What we're going to look at today is what if one of these boundaries, a or b, is not a finite amount but is infinite. And that is what we call an improper integrals. Now there's other types of improper integrals too. We're not going to look at those, but just notice that if you were to look further, there's other places where this would apply as well. But we're just going to look at changing the interval to either minus infinity to b, or we'll go from a to positive infinity. Actually, you can't have a bracket on infinity, right? It's a parentheses because you never really get there, okay? Because we're going forever. And maybe I can emphasize that this is positive infinity, okay? So that's what we're going to look at. Integrals in which a limit of the integration is indefinite. It goes on forever. Now let's take a little bit of review. We're going to go step back to 10.3. So remember, I told you as we go through this last two chapters, we would touch on everything we've learned. And remember, 10.3 was limits. So we're going to bring a little bit of that into what we're doing today. So we're going to look at a few of the determinate, indeterminate forms we came up with. So this is a little bit of review. If you want, go back to section 10.3 and review it a little bit more on your own. One of the things we came up with in 10.3 is if we have a polynomial rational function, polynomial on top, polynomial on the bottom, something like 2x squared plus 3x plus 4 over 7x to the 17th plus, something, 2x, whatever. Okay, that all we need to, that what this tells us is all we need to do is look at the biggest degrees. Okay, so all of these are smaller. So in this case, all we'd have to do is come look at the biggest degree in top, the ratio of the biggest degree in top to the biggest degree in the bottom. We'd look at that limit, and that would tell us everything we needed to know about what happens at infinity. Okay, so again, go back and review this section. Unfortunately, there's no videos because we weren't on remote mode at that time. But so maybe anyway, it would be cool. Maybe by next year I'll have videos for each section so that could be reviewed too. But this is what we're focusing on. This is all we have to worry about. So this gave us some sort of quick ways of looking at things. So if we had some number over 0, either coming from the left or the right, remember, that diverges. We'd call that diverges because it'd go off to infinity. Diverging means it doesn't stop at a number. It just keeps getting bigger and bigger. If you have a number times infinity, well, that's also going to diverge off to infinity. A number where you add or subtract infinity, you also go to one of the infinities, either positive or negative. So those are the quick, what we call determinate forms. Now the indeterminate forms, if we end up with like 0 over 0, we don't know what's going on. Infinity over infinity, we don't know what's going on. Those ones, there's other tests, but we'll see in the examples we do, will probably be in the realm of one of these determinate forms. Okay. Also, if you end up with something going to infinity on top with some sort of constant in the bottom, that also goes to infinity, right? But when you have like a constant number on top divided by infinity, or something going to infinity, that actually goes to 0. Okay. And then if one more sort of set of things, if k, the number here, if it's greater than 1, then what happens as the exponent goes to infinity, so does the result. Okay, it just keeps getting bigger and bigger because k is bigger than 1. When k is less, or say k is still bigger than 1, notice a negative exponent means that it becomes a fraction, so it kind of becomes like this case up here, then it goes to 0. Okay, let's see, did they give the case where they didn't? So we could also swap these, since they didn't give it, if k is less than 1, so it's like a decimal, then k to infinity, to positive infinity, that's what goes to 0, and k to negative infinity, because again, that's a reciprocal, so now it's no longer a decimal, that goes to infinity as well. Okay. Now k itself, so actually k itself is not going to be negative. I should put this extra constraint on it that k is bigger than 0. Otherwise, it doesn't make sense. K not equal to 0 because that's not an exponential. Okay, just a few things to review. Now let's get into our actual lesson for 14.5. So integrals where the limits of integration are infinite. So here's going from a to infinity. Here's coming from negative infinity to b. We could go from negative infinity to positive infinity. I think we overlooked that one. We don't have an example where we're going to be doing that because it's not in the homework. Okay, but this, because in business we usually have a starting point, and then what we want to see is some undetermined time in the future. We don't know when it is. We're not really planning for forever, but as far as we know, we're not giving an end point. What if it happens indefinitely? That's what we're going to use as business folks when we talk about infinity. The case for the B is something has been happening so long we don't know when it started. So that's kind of what we would use this negative infinity to, maybe current date or to some date in the future. We'd want to kind of see maybe what's been happening in a situation where we don't know when it started. That could happen. Okay, so what we're going to use are limits. We're using the limits as something gets large, and in this case what we're looking to get large is time. Okay, so here we're going to define, and in math we just do this. We define it, we say it, it's like an executive order. It's just true because we say it's true. Okay, oftentimes there's science and evidence behind things, unlike some of the rules and regulations we get in our regular life. But what this is saying is that the limit as it goes to infinity, what we do is we pick some arbitrary m, and the good news is we don't have to know what it is. It's some number, and then what we're going to do is we're going to integrate it from a to m, and thinking of m as a fixed number. So all our theory, all our things we've done before with definite integrals applies. And then what we do is once we integrate, we take that limit, we take that unknown value m, and we let it go to infinity, and then we see what happens. So it will either converge, so it goes to a number by using one of our examples, or it just gets really big, or it gets really small. It shoots off to infinity is what we would say. Then it would diverge. So one of two things happens. If it diverges, that's all we can say about it. it diverges. We could say whether it goes to positive or negative infinity sometimes. But if it converges, we could actually come up with a number, and that's what we're going to do. Okay. So we do the same little trick when we're starting from infinity and coming to a particular point. Again, we didn't know when this situation started, so we figured it's always been happening. So what we do is, again, we take some value, unknown value, we make it a variable, but it's in our minds, it's a fixed amount. And then what we do is after we integrate, we let that fixed amount, we let the limit of it go to infinity, in this case, negative infinity. Okay. And again, we won't be doing this, but this one, what we have to do is sort of pick some arbitrary point A. And basically, since we know how to do this one and the one before, notice this one fits sort of here, the one we did before from the other page, I'll just kind of bring it in, fits there. So we've talked about these, we can do each separately, and then we could add them together. Now, if one of them diverges, remember, one goes to infinity, the thing diverges, it doesn't matter about one. So we would need both of these to converge to be able to get a number. Okay, hopefully this all makes sense. Again, it's a bit abstract as we're going, but you'll see, both have to converge. And then that kind of makes sense, because if one diverges, it will, okay? All right, so here's an example. And they just work through it all. So we've got this integral going from 1 to infinity, okay? 1 over x squared. So when we integrate this, right, and again, you want to think of this as x to the minus 2. Okay, so they rewrite it with a limit. Notice they, instead of writing the infinity, they make it some value m. And when we integrate this, again, thinking of it as x to the minus 2, remember we add 1 and then divide by the new exponent. So that's going to give us x to the minus 1 over minus 1, which they've rewritten as 1 over x minus 1 over x. Okay, the limits of integration are from 1 to m, so they plug those in. So first they plug in m, so that's that part, and then they subtract, plugging in 1. So what they did is, since we have minus 1 over x, just what you see here, minus 1 over m minus 1 over 1. Okay, so the negative became a positive, that's what happened there, and 1 over 1 became just 1. Okay, so that takes a little bit of the mystery out. Now what we do is we take the limit of each of these. Well, the limit of 1 is just 1, but what's the limit of 1 over m? Negative 1 over m. Well, as m gets really, really big, right? And again, it's going towards positive infinity, this becomes 0. Okay, that was one of our rules that we looked at from 10.3. It says something getting really big in the bottom, that this goes to 0. So we end up with, from up here, 0 plus 1. 1 has nothing to go to infinity, it's just a fixed, so it goes to 1. It converges, okay, because this part here converged. Okay, that's all there is to it. All there is to it. So that's how we get convergent. And trying to think of what this looks like. Why does it converge? Well, let's do something nicer than that for you. Let's come back here. Let's go to Desmos, a good friend. Because remember, we're getting the area under a curve. So what was the curve? It was y equals 1 over x squared. Okay, and we were going from, I can't really write here, but from 1 to infinity. So what you're seeing here, Let's zoom in a little bit more. There we go. So we're getting this area under this curve. And again, while the function never actually touches the x, it never goes to 0, it's getting so close, even though it goes on forever, the area goes to 1. This is it's what I call anti-intuitive. There's a word I made up because it just seems weird. You would think that something goes on forever, you keep adding a little bit more, would actually go to infinity. But there are some other physical ways you could look at this. But bottom line is this area, what we add on, gets so small it doesn't add anything of importance. So we can say it goes to 1. Okay, that's what's going on here. But it's taken me years. I read books on infinity, and if you read a mathematical book, there's one I kind of liked. It was called Keys to Infinity. Can't remember the author. It was about 20 years ago, but it was almost like a religious book. A mathematician writing about infinity. I guess that's kind of where you see religion, or you get the spiritual sense to mathematics when you start talking about infinity, because certain things you have to start taking on faith. Anyway, I thought it was kind of a cool journey for myself. Read any mathematical book about infinity, and you get to understand infinity as not just this thing that is way out there in the future that we never get to, but you actually start dealing with, well, what if we actually got there or got close? It's kind of cool. Okay, so now that's all we got to do is we sort of do this trick where we say it's going to go to some finite limit, use limits to get there, and then just we see it will either converge or diverge. And typically what we're going to see is it will convert. The part with the infinity will go to 0, which means it kind of gets out of the picture, or it will diverge. Okay, so here's an example. So 2009, music downloads are making serious inroads into the physical CDs. So approximately 290 million CD albums were sold in 2009. How many of you guys even know what a CD is? Maybe they were still selling them in 2009, I guess. I'm thinking of vinyl records. I know a lot of you were born after vinyl records had already died, but anyway, in 2009 there was a steep decline, about 23% per year. So suppose at this rate, again, this is just looking in the future, so this rate of decrease were to continue indefinitely. So we're going down by 23% each year. Now the idea is that we would never completely run out, but obviously there is a time when CD albums would sort of stop to be sold. But in 2009, we don't know when that's going to be. So what we can do is we want to see what's the total sold. That's an integral, right? A definite integral, but in this case, an improper definite integral, because we don't know when the day is when CDs will no longer be available. So we want to, between 2 days can be computed. So what we're going to do is we're going to go between 2009, which we'll call year 0, and some date in the future, which we don't know. We'll set it as infinity, and that gives us the indefinite part, and that will tell us sort of from 2009 to that date what's the most CDs that are ever going to be sold. And this is important if you run a CD factory. You say, well, let's see, how many more are we going to get sold out of here? So what's our function? Now remember, it's a 23% decrease, and going back to our algebra, that means we subtract from 100%. So that's going to be 0.77, and it'll be an exponential because each year we're only getting 77% back. And then we multiply by what we started with, which is on the other page, and they'll come up with this. So it's the starting value, I'll just call it P, times 0.77% to the T. That's what our rate function is. When we integrate it from 2009 to infinity, we will get the total that will be sold, unless it diverges, which it probably won't, right? Because this is a k value less than 1, right? So we haven't done one of these yet, but how does this integrate? Remember, it integrates into itself. Constant multiplier comes up front. But with this, with e, we just got e to the t, right? But with this, we get the natural log of 0.77. Okay, so that, we didn't do a lot of those, so maybe that's, anyway, here it is, okay? And again, we're going to go from 0 to m, and then we'll take the limit of this. So they're going to keep going here. I should get my stuff out of the way, but you'll see that's basically what they came up with. I forgot where they were going, okay? And then, so we come to the next one, we let it go. Notice this is the integral, what we got, 290 over natural log of this. This is just a number, and we'll find out, we'll actually calculate it. This is going from 0 to m. So you plug in, here it is, the next, plug in m for the exponent here, and 0 here. Anything to the 0 power is 1, so this part's going to become 1. And notice as we look at this limit, let this go to infinity. Remember, that's also one of ours. When k was less than 1, the exponent going to infinity means it's getting smaller, smaller, smaller. This actually goes to 0 as m goes to infinity. Okay. So it just disappeared. So there's a minus here. There, that's where the -1 comes from. So it's just this number times -1. Now you might think, how could I have negative sales? Well, you're going to see a natural log less than 1 is also negative. Negative times a negative is positive. So let's go ahead and see, do I have natural logs on here? I do. So we've got 290 divided by the natural log, not of 290, let's go back. So 290 divided by 0.77 natural log, that's the way this one works, times -1 gives us a positive 1,000. How did that? I didn't. 1,109. They rounded it up to 10 because they wanted it right. There's a 9.5, so the 5 rounds up to 9. So we could expect that by the time CDs stop being sold, there'll still be another 1,110,000 CDs to be sold. Again, to make some assumptions, but that 23% will continue. Now, if it picks up, then all bets are off. So, but at that rate, that's one type of mathematics that this owner of a CD factory could use to make a prediction of should we stay in business or not. Okay, so what I'm going to do now is, yeah, we'll discard these. There wasn't that much. That's our lesson. I'm going to do a few short videos with some other examples, but basically do the integration like we've always been doing. The part that's infinity, let that be some letter. It could be m. Go ahead, stick with m. And then let that part go to infinity after you've done all the integration. And if it diverges, it diverges. So I'll pull up a few examples, and I'll do at least one that diverges so you can kind of see that one. And then we'll be good to go. Thanks.